When we talk about confidence intervals, you've actually probably seen examples of confidence intervals plenty of times in the past. If nothing else, you've read a newspaper article that might refer to polling data. And it turns out that that is a confidence interval, but it's not as simple as you might think to interpret what that confidence interval is saying. And interestingly, a lot of the news articles you read about it don't quite interpret it correctly either. So part of what we'll be doing today is talking about how to construct those confidence intervals, but part of what we're going to be doing is talking about how to interpret them correctly. What do they actually tell us? Okay. And before I go into the details of what we'll see in each portion, I just want to give a big picture idea that confidence intervals are when we don't know something about the population, but we've collected a sample, and we want to use that sample to estimate what is happening in the overall population. So that's exactly what polls are doing. If I don't know what percentage of the voting population supports this particular political candidate, I might run a poll and see. And of course, I know that whatever I see in that poll is not guaranteed to be the exact same number that's true of all voters. If I see that 72% in my sample support it, that doesn't mean that 72% in the population do. But it does tell me that it's usually going to be pretty close to that 72% number, within a certain region of variability. And when we report that, that plus or minus margin of error portion is actually capturing that variability, and that's what we're doing today. We're going to be talking about how to construct what that window is that we can be fairly confident contains the correct value. Okay? It doesn't mean that it has to. You never know what your poor luck might be. You just happen to get a handful of people who are particularly supportive of this candidate or particularly opposed to them, and so the results you saw were unexpectedly low or unexpectedly high. That can happen, but depending upon what level of significance you choose, it should be a rare event. Okay. All right. So in our discussion today, we will have three portions. It's possible, we'll have to see, it's possible we won't have time for this third portion. If we do, great. If we don't, then I'll push that to next week. But first we're going to talk about confidence intervals for proportions, and that's actually exactly where that polling idea comes from. If I want to know what percentage support someone versus oppose them as a political candidate, that is a proportion that I'm trying to estimate in the general population. So I can build a confidence interval for proportions to tell me, based on my sample, based on the poll that I ran, how much support do I expect to see in the general population. Okay. As part of that, we'll talk about the trade-off that we have to make between being certain that the correct value is in our window versus having a small enough window that we actually get usable information. I mean, I can certainly tell you that the support for this candidate is guaranteed to be between 0 and 100%. But that's not very useful information. And even if I can tell you that it's between 25% and 75%, it's still not very useful to know that. I have no idea if they're ahead or if they're behind in that situation. So being more precise can give us more information, but it also introduces some uncertainty because obviously our particular poll is not guaranteed to be 100% representative of the overall population. And that's true just because of sampling variability. There's nothing I can do to avoid that possibility. What I can do is try to limit it through what I know about probability and statistics, and we'll talk about some of that today. After we've done confidence intervals for proportions, we'll then talk about confidence intervals for means. And so in that situation, I'm trying to estimate the mean of a population that I don't actually know up front. And the best way I know to estimate that is by collecting a sample, finding the mean in the sample, and then using that to construct a confidence interval for the population as a whole. As with proportions, I'm not guaranteed to contain the true value in that window, but I can control the likelihood by using what I know about probability and statistics in much the same way that I did up here. And in this portion, we'll be talking about a situation where we know the standard deviation of the population. Okay. That makes our life a little easier. It turns out in both case 1 and case 2, we can use the normal distribution because of the central limit theorem. However, in practice, it is often very difficult to know the standard deviation in the population if you don't know the mean. Right? We know how that's calculated. It's calculated by subtracting the mean, squaring those things, and then finding the average deviation from the mean. Well, if you don't know the mean, then how are you going to know the standard deviation, right? Theoretically, it's possible, but it's very rare. And so in practice, we actually have to do something a little different when we don't have access to that standard deviation. We have to use a slightly different distribution. It's one related to the normal distribution, but it's a little different, and it's called the student's t-distribution. So we'll see that here in this last portion, and we'll build confidence intervals using it that will be very, very similar to what we built in section 2, but will be a bit more accurate and very useful even with small sample sizes. Okay. Any questions about that plan? All right. As always, don't hesitate to interrupt me during the discussion if you have any questions at all about what we just talked about, or if you see something that connects to what we talked about before, or you're trying to figure out where it goes. I'm happy to answer those questions in real time. I think it tends to make it easier to follow when students ask when they have a question. So in order to kind of give you the picture about why this matters, I did want to show at least one example where the newspaper article reporting on a particular poll didn't quite capture the true information. Okay? So this is a recent news article about Americans' perceptions on the theory of evolution. Okay? And in this article, it says that 60% of Americans say that humans and other living things have evolved over time. This is a Pew Research Center poll. 60% say that this has happened. 33% reject that idea, saying that they have existed in their present form since the beginning of time. The survey included almost 2,000 adults across all 50 states and ran for, 2.5 weeks. The margin of error was 3 percentage points, and the way the newspaper article reported this is saying that the margin of error means that the results could vary that much either way. Now, there's a number of things here, but in particular, that last statement is definitely not correct. Okay? The margin of error being 3 percentage points does not mean that the true support level for the theory of evolution is between 57 and 63%. This poll could have inadvertently been inaccurate. They could have just happened to choose 1,983 adults who particularly supported the theory of evolution versus particularly did not support. And therefore were not 100% accurate in reflecting the views of Americans as a whole. What we can do is we can talk about what that margin of error actually tells us. It tells us a likelihood, a likely window in which those support levels actually fall. So I want to highlight the kinds of things we'd like to say and that you might often see said, and which ones might be true and which ones might be false. So based on the results, we found a sample polling percentage of 60% who believed in evolution. So we'd like to say exactly that. 60% of Americans believe in evolution. Is that what this poll tells us? What do you think? The poll found 60% believe in evolution with a margin of error of 3 percentage points. Well, if you're going to guess, you've got a 50% chance either this is a true statement or it's a false statement. And generally when trying to decide whether a claim is true or false, it's a little harder for it to be true because there are so many ways it could be false. Even one part being incorrect or being missing would make it false. So if I had to hazard a guess here and I didn't know anything up front, I would guess that this is false. That's correct. Does anyone know why? What is false about this? Why is it not true that from this poll I can conclude 60% of Americans believe in evolution?
Is it just because the sample that you've taken is only in that sample, so you can take another sample and that can be totally skewed a different way?
Right. Even if this is a great sample and it's very representative of the true value, I wouldn't bat an eye to see 61% as the actual number in Americans, or 59%, right? Those are all perfectly in line with the 60% number coming from this poll. So I certainly cannot claim that 60% is the exact number among the population just because that happened to be the number in this particular sample. Sampling variability tells me I expect a little bit of variation. They should be clustered near the true value, but there's going to be some variation from one poll to the next. If I poll 2,000 Americans this month and 2,000 Americans next month, I'm going to get different numbers, not because their attitudes as a whole have changed, but just because there's random variation from one poll to the next, right? Just the luck of the draw with the sample that I happen to collect. So that 60% is just the proportion observed in the sample, and because of sampling variability, this may not be the exact correct value. Maybe it is. You never know. Since I'm rounding to the nearest percentage, it could be that 60% is correct. All right, well, here's another thing I'd like to say. It's probably true that 60% of Americans believe in evolution. Sounds like I'm hedging my bets a little bit here. Does that make it not false anymore? Okay. Well, no. This doesn't help us at all. Simply saying it's probably true, it's actually probably false, because that's a single number, and sampling variability tells me I'm going to see things on either side of the true value every time I do a new poll, right? I might see the actual exact value, it's possible, but I might see 61%, I might see 60.2%, 59.8%. Each of those things is just slightly different than the 60% that's being claimed here. So I can't even say that it's probably true, because in fact, if I were actually doing a probability estimate, it's probably not true. But it's probably close. Right? And that's really what we want to be able to say here. All right. We know that between 57% and 63% of Americans believe in evolution. This comes from that 60% with a margin of error of 3%. What do we think about that?
It's still false.
Yeah, still false, right? Most of the time, in a way that we can quantify, and we will in just a few minutes, most of the time, this will be true. Most of the time, if I see 60% in my poll, and I have a margin of error of 3%, then the correct value will fall somewhere between 57% and 63%. But that is not all the time. It is not guaranteed that it will fall in that window. And that was actually the mistake that was made in that newspaper article summary. They were claiming that the margin of error of 3% guarantees us that it's within those two values. It does not. But it does give us a likelihood. In fact, in most cases, this is a 95% confidence interval, which means 95% of the time, if I collect a poll in this manner, the correct value will fall between 57% and 63%. So 95% of the time, this will be a correct statement, but the other 5% it won't be. And so therefore, we cannot say that we know this is true. It has a 95% chance of being true, but that does not make it the case. Okay. All right, questions about that? So each of these things are statements that we might like to say, and that you probably will hear some people say when interpreting confidence intervals, but none of these are quite right. And it's because of a misunderstanding of the nuance of sampling variability. Every time I collect a sample, I may see a slightly different result. We can quantify what we expect to see by using the central limit theorem with the sampling distribution that we saw last time. So if you'll recall, we can actually figure out what the standard error for the sample proportions will be. And we would expect them to be centered near the true value, and then from that we can construct a likely window. That's actually what we're going to be doing next. Now before we do that, I have three different things here that are not correct interpretations. So it would be good to know what the correct interpretation is. Okay? And so here, let's slow that down a little bit so you can see better. What we can say, if it's a 95% confidence interval, is that we are 95% confident that between 57% and 63% of Americans believe in evolution. So this captures the 60% we saw in the sample right here in the middle, and the margin of error of 3% on either side. And it also makes clear that we're relatively confident, we feel pretty sure that that's correct, but we allow for a 5% chance of being wrong, right? There's a 5% chance that, in this case, Well, I shouldn't say it that way. It either is wrong or it isn't wrong. It's not really a chance in that sense. But 5% of the time, if I constructed a confidence interval in this way, I would actually end up constructing an interval that did not contain the correct value. Right? It just happens by random luck sometimes. In this case, 1 out of every 20 times. And so I can't guarantee you that I'm not looking at one of those 20 times. Okay. All right. So how do we construct? Construct a sampling distribution to figure this out. And this will be key to what we end up doing when we construct these confidence intervals. I need to have a way to figure out where the middle of my sampling distribution will be and what the spread will look like in the form of the standard deviation of this distribution. Well, we can compute the mean as being identical with the population mean. Right? So if I expect the population mean to be P, whatever P might be, I can then figure out from that middle how far away I expect one standard deviation of the sampling distribution, 2 standard deviations of the sampling distribution, and so on to be. So I can construct a normal distribution for samples. They'll be centered around the true value, the actual population value, which up front I don't necessarily know, and they'll be spread around that following a normal distribution. Okay, this is again coming from the central limit theorem that tells me that I can expect that. This particular example, when I compute that standard deviation, it's always the square root of my success rate or support rate times my failure rate or opposition rate divided by the sample size. So this gives me the equivalent of standard deviation for this sampling distribution. And so in this particular case, if I computed it and found that that number was 0.37, then this would be the way I would construct that distribution. It'd be centered around the true population proportion, and within 1 standard error, that's 0.37 of it, I would find 68% of all sample values. Within 2, I would find 95% of all sample values. And so when I construct a sample, a confidence interval from this, if I want to be 95% confident, I would have to include this window right here, between 2 below and 2 above the value that I computed. So that's exactly what we're going to do. We're going to figure out how to go from the sample value I observed to constructing 2 below and 2 above to get a 95% confidence interval. In order to do that, I need to know what z-score corresponds to a certain percentage of the middle area, right? That z-score is called a critical z-score. And so if you think back to the empirical rule, we talked about within 1 standard deviation we find 68% of all values. Within 2 we find 95% of all values. And within 3 we find 99.7% of all values. So if I wanted a 68% confidence interval, I would want to go from a z-score of -1 to a z-score of +1, based on that reasoning. And so my critical score would be z star equals 1. I want within 1 standard deviation. If I want a 90% confidence interval, I have to think about how to get that. You can do it with technology if you'd like. But if you do, the middle 90% is between -1.645 and +1.645 as a z-score. So between 1.645 below, 1.645 standard errors below, I should say, and 1.645 standard errors above. So that captures the middle 90%. And I know I said, based on the empirical rule, that the critical score would be 2 if I want 95%. But like we saw in the example before, if I use 2, I actually get a little bit more than 95%. I get 95.45%. If I want the actual 95% confidence interval, I need to be more specific. It's not exactly 2, it's 1.96. So within 1.96 standard deviations of the mean, I will find exactly 95% of the area. Okay. Just to show you that, how to find it, because you will have to do this in a few places. Let's go to the normal distribution. standard normal, I should say. And what I want to do is I want to find the critical score for the middle, whatever percent I'm looking for. For a 68% confidence interval, it should be within 1 standard deviation. So let's type in 0.68 and see what it tells us. Within 1 standard deviation, I find, well, within 0.9945 standard deviations, I'll find 68% of the area. If I go within 1 standard deviation, it's not exactly 68, it's 68.268%. Right? We typically don't construct a 68% confidence interval. I was just showing that to you so you can see where it comes from. Now, if I try to use 2, within 2 standard deviations, my empirical rule estimate says 95%. We can see that's a little bit bigger than what I want. So let's change it to make it exactly 95% and see what the boundary for the 95% in the middle happens to be. 1.95996, and so you can see why that is reported as 1.96 is my critical z-score. What if I want a 90% confidence interval? Well, then I want the middle 90%, and 1.645 was the number I reported on the slides. Technically, it's 1.64485. Okay. And feel free to use the more accurate number here if you'd like. Let's see, what else might I want to do? I might want to do a 98% confidence interval. So if I type in 0.98, I need to use a z-score of 2.3264. I do recommend using at least 4 decimal places with that z-score, because what we're going to do is take that z-score and multiply it by the standard error to compute the margin of error, and so any rounding in the z-score will be compounded by that multiplication process. Keep as many decimal places as you can. My suggestion is don't round until the very last step. Okay. All right, questions about what these critical z-scores are doing? If I want to find the middle X% of area, I need to know what boundary points to use for that, and the z-score corresponding to that boundary is the critical score. Okay.
I have one question in regards to, you had said for just the basic z-score, you call it just z-score, and then to get the 95th percentile, you call it critical z-score. If we were going for the 98th percentile, do you have another term for that?
No, it's still the critical z-score. It's critical for the particular confidence level you're looking at. That's a good question.
Fantastic.
And that's part of why I'm showing you this process, because when you read a question for a confidence interval, the first thing they'll have to tell you is what confidence level do we want.
Okay.
If we want 95%, then the critical z-score I'll use is 1.96. If we want 98%, the critical z-score I'll use is 2.3264. And you can always find more decimal places by using this calculator, or one that actually reports more decimal values. If you have one of the TIs, I think what you want to use is inverse norm. That will take an area and from it compute a z-score, and that'll allow you then to find the critical z-score you're looking for. Okay. All right, good questions. Any other questions before we jump back into confidence intervals? Okay. So the critical z-score tells me how many standard deviations I need to collect to have that amount of area in the middle. Okay. If I want 90% of the area in the middle, I need to have 1.645 standard deviations on either side, and that will give me the middle 90%. If I want the middle 95% for a 95% confidence interval, I need to use a z-score of 1.96 to collect almost 2 standard deviations above and almost 2 below. Okay. All right. Once I've done that, the margin of error telling me how far above the middle to go and how far below the middle to go is just my critical z-score times my standard error. So the critical z-score is computed the same way I just showed you here. And the standard error is computed by that formula. You take the square root of p hat times q hat over n. P hat is the sample success rate, q hat is the sample failure rate, and n is the sample size. So in my poll of 1,983, I think it was, U.S. adults, I would use n equals 1983, and the p hat there was 0.6, and the q hat was 0.4. So 0.6 times 0.4 would be what, 0.24 over 1983. Take the square root of that, that'll be the standard error, and multiply it by, well, 1.96 in that case, because I wanted a 95% confidence interval. And that should give you a margin of error of 3%. In fact, let me just check that real quick, because now that I know those numbers. Always dangerous to do this without having done it beforehand, but... Alright, so that's times 1.96. Oops. So I get a margin of error that's a little bit bigger than the one they had. 0.0215, or a little bit smaller, I should say. So, interesting. So I wonder if they used 90%, or 98%. 98% is what, 2.32? Six. 3264. Yeah, that's a little closer. That would at least round to 3%. All right. So key idea, once you know the confidence interval, you will know how many standard deviations in the middle you need to collect. That is, how many above the mean, or how many above the middle, I should say, and how many below the middle. The margin of error is that critical z-score, so that's how many standard deviations, times the standard error, which is the equivalent of the standard deviation. And in this case, that's the square root of p hat times q hat over n. Okay. So let's construct one. Suppose I have a survey, and this actually did come from real numbers, on the approval ratings of Congress. This is the U.S. Congress, of course. And this survey had 230 respondents and found that 19% approve of the job Congress is doing. They are very popular. In fact, if anything, the numbers may have fallen since that point. Find and interpret a 95% confidence interval for Americans' overall approval rating of Congress. All right. So, let's see, what can we do here? I need to compute my middle for my confidence interval. That's going to be what comes from my sample. And then I need to allow a certain amount above that, a certain amount below that. The amount there is called the margin of error, to capture the middle 95%. In order to do that, I need to compute the standard error and the critical z-score, and then multiply those two things to get the margin of error. All right, so let's get started here. What do I know? I know that I've sampled 230 respondents, and that the support rate in my sample is 19%. I also was told I want a 95% confidence interval. So what's the z-star for that? You want to remember?
1.96.
Right. 1.96 is slightly more precise than the 2 that we reported with the empirical rule. Okay, so that gives me my critical z-score. I need to use this and this to compute the standard error for my sampling proportion. And remember the formula for that is p hat times q hat over n, all under the square root. Alright, so again, what we know, p hat is 0.19, q hat is what?
1.96.
Nope, that's the z-star. What's the q hat? think about it this way. When I do a proportion, I need to know which are in one group and which are not.
0.79,
0. What again?
79,
No, not quite. I have 19% support Congress. What percent don't support Congress?
0.81, 81%.
81%. There we go. And my sample size is 230. And so from there, all I need to do is to calculate that. Plug that into my calculator and see what I get. 0.19 times 0.81 over 230, and then the square root of that. I get 0.025867. When you do these calculations, keep the number you get in the calculator. The calculator is going to store a lot more than I just wrote. And so when I multiply that by the critical score, I'll have more accuracy. And then I can round in the very last step. It's a good rule of thumb in general in a math class, if you're reporting a rounded answer, to wait until the last step to round. This is particularly important with confidence intervals. Okay, so I have my standard error. Remember, I want the margin of error. And that's always my critical score times my standard error, which is 1.96 times this number, 0.0258, ... I'm going to use the number that is still in my calculator, so it's more accurate. And I get 507. And then there's actually 0041. That's just a rounded value, but that should be close enough. So my margin of error here is about 5.07%. My middle is the p-hat value. That's the 19%. And so my confidence interval is going to be the middle value, the one I found from my survey, plus or minus my margin of error. Which we would report as 19% plus or minus 5.07%. That means if I was reporting on this survey, I would say, and this is the correct way to interpret this, we are 95% confident that the support level for Congress is between, well, let me do this really quickly, 13.93% and 24.07%.
Can you scoop that up just a little bit higher?
Absolutely. Actually, just rewriting here because I'm going to show you other ways to write the same result. So my confidence interval can be written in three different ways. One is 19% plus or minus 5.07%. Another is as an actual interval, like an interval notation. So it's the interval from 13.93%, which is 19 minus 5.07, to 24.07%, which is 19 plus 5.07. If I take the midpoint, subtract the margin of error, I get the lower limit. Take the midpoint and add the margin of error, I get the upper limit. So that's my interval. And there's also a thing called tri-inequality form, which says that my true value is somewhere between these two numbers, and the two numbers are the same two numbers that are in the interval notation. So it's 13.93 and 24.07, at least when reported as percentages. as a proportion, I might record it as a decimal, or I might record it as a percentage. Either way is okay, just make sure you know which one the question is asking for. All right. Questions about that one example? We will do more, but I want to show you a couple of things about what we did here and how it changes from one example to the next. Sherry, do you have a question?
No, I'm sorry.
That's okay. All right. All right, then let's jump back in. Let's check and see if our results lined up with what I had in the slides. All right, great. I didn't look at this beforehand, so it's good that it always works out. It is between 13.93% and 24.07%. Okay? And the way this is usually reported in the news article would be that the support for Congress is 19%, with a margin of error of about 5%. And we should know that that means we are 95% confident that it's between 14% and 24%. All right, but we don't know for sure. There's a 5%, well, 5% of the time, this survey would reflect a true proportion that's actually outside that window. It might be less than 14% or more than 24%. All right, just random luck. We happen to poll people who particularly liked or disliked Congress. All right. So this is just defining the things I've already shown you. The margin of error is how far on the right and how far on the left of the midpoint that my confidence interval extends. So it would tell me how far above the middle and how far below the middle I want to allow to capture that middle X%, whatever it might be. If I want a 95% confidence interval, I want the middle 95% of the area. So the margin of error tells me how far to go, and the number of standard errors that that represents is what the critical value is doing. It's saying how many standard errors do I need to go to capture that middle X%. Okay. So that's where we're connecting that critical value. Z star is 1.96 or Z star is 1.645, etc. It depends on the confidence level, but that will tell me how many standard errors to collect. I multiply that by the standard error, and I get the margin of error. This is just an example. If I want a 90% confidence interval, then the critical score I use is 1.645. As we saw in the previous example, if I want a 95% confidence interval, then I'll use a 1.96 critical score. Different confidence levels produce different critical scores, and therefore different margins of error. So thinking about it that way, with the same survey, the same data, I can construct different confidence intervals for different levels of confidence. How does that have an impact? What happens there? So suppose I want a 90% confidence interval. Would my margin of error be bigger or smaller than it is for a 95% confidence interval? Let's take a look. Basically, what I'm doing with this confidence interval process is I'm trying to take the data I've collected and then build a wide enough window around that to capture the true value somewhere in between those two bounds. Now, there's a trade-off between making that wider and therefore more likely to collect the correct value and being more precise, that is, having a better estimate. Between 14 and 24% supporting Congress, that's relatively tight. I have a pretty good picture that they're not very popular, right? But if my bounds were between, say, 46 and 54%, I really don't know if people support them or don't support them. It's really just kind of middle of the road. It's hard to say. So even the same kind of window can look a little different in different locations. If I want to be more likely to capture the true value, I have to extend that and make it a wider window. I have to have a larger margin of error, and the result is then I have to have a larger critical score, a larger number of standard errors. On the other hand, if I want to be more precise, I can certainly do that, but when I do, the cost is I'm slightly less confident that my confidence interval contains the true value. If I want to use 1.6545 as a critical score instead of 1.96, I can do that, but then my 95% confidence has to be reduced to 90% confidence. And so that's what happens here. There's that trade-off between being more confident with a wider window and less confident, but with a more precise estimate. Okay. Now, one thing that often comes up, if I am going to be doing a poll of voters and I want to see if a particular measure will pass, I might say, well, I want to find the true value with 95% confidence with a margin of error no larger than 2%. Right? I feel like if I can do that, I can have a pretty good picture of whether this is going to pass. Okay. How do I do that? Well, without having collected the data, I can't even compute the standard error. So even though I may know my critical score, I can't produce the margin of error without that standard error, and I can't produce that without actually knowing what already comes out. But there's a neat feature that comes from maximization problems if you've done these in algebra. You remember how when you find the area of an enclosed pen with a fixed amount of fencing, it turns out that the way to maximize area is when all sides are the same, when that rectangular pen actually becomes a square. It just happens to somehow maximize the amount of area you get for the same amount of fencing, right? That symmetry plays out in lots of different places. It actually plays out here as well. The worst case for the standard error, that is when the standard error is the biggest, happens to be when the support rate and the failure rate are the same. When you have that symmetry, they're both 50%. So that's the worst case for the margin of error. If you want to guarantee a margin of error no larger than 2%, what you can do is you can use this worst case, plug in 0.5 and 0.5, plug in your standard, plug in your critical score, and then solve for the value of n that gives you that particular margin of error. So you can actually find how many people do I have to survey to guarantee that I get within 2% as a margin of error in a 95% confidence interval. Okay. This is again showing the same ideas just from a different perspective. That critical value is telling you what bounds, the negative of it to the positive of it, will collect the middle confidence level percent of the area. So if I want a 90% confidence interval, I want that middle 90%, so I want this area to be 0.9. And I can find that that happens when my boundaries here, symmetric on both sides, are at negative 1.645 and positive 1.645. So that's why we say the critical number is 1.645. That's how many standard errors I need to go beyond the midpoint to get the upper limit. It's also how many standard errors I need to go below the midpoint to get the lower limit. So it tells me exactly how far on either side I need to extend. If I'm using 95%, again, the critical value is 1.96. There are other values out there. Those two are probably the two most common. But on some of the homework questions, you might have to use 80%, or you might have to use 98%. You can compute the corresponding critical value from Wagnar's calculator, or from your TI, or any of the other calculators you like to use. Make sure to use your basic reasoning and realize that if I want more confidence, then I'll have to collect more standard errors, so my critical value should go up. For a 90% confidence interval, my critical value is 1.645. If I want to increase that confidence level to 95%, I have to widen my window, so I have to collect more standard errors, and that's why it goes up to 1.96. If I want to collect 98% in the middle, it'll go up even further. I think it was 2.32 we saw a minute ago. On the other hand, if I want to collect the middle 80%, then I can actually choose a number smaller than 1.645. I can use Wagnar's calculator to figure out exactly what it is, but it's between 1 and 1.645. I'm going to guess just offhand roughly 1.4-ish. But you should compute it in the calculator to find the exact number. You can always use your reasoning to make sure you're collecting the right value. If I want more confidence, I need more standard errors, and so my critical score has to go up. My critical value has to go up. All right. So help me out with this. Suppose I want a 76% confidence interval. How would I do that? How would I find the critical value for that? Well, the first thing I want to do is I want to use the standard normal distribution. And I want to collect the middle, was it 76%? I just type in 76% here. And there's my middle area being 76%. It looks like it happens when my critical value is 1.175. Check that. Slides. Oops. All right. So between negative 1.175 and positive 1.175, that means my critical value is 1.175. You can do that either by using the standard normal calculator, the way I just showed you, or you can find the place where the area below it is, well, the 12%, or the area above it is the 12%, because that will capture the middle 76%. Any of those things are valid ways to do it, and if you draw the picture, if you draw the picture, I wanted. Sorry, here it is. This middle area being 76% means this area is exactly half of that, which is 38. And of the 50% on this side, if 38% is here, 12% is here. So how much cuts off the upper 12%? Should be the same value. Oh, that's the lower 12%. 1.175. The upper 12%. Positive 1.175. So when you draw the picture, you can figure out how the geometric regions add up to 1 as a total. You can find multiple different ways to get the boundary points. And all of them come from going from an area to a boundary value, which is the reverse of the normal distribution calculator. So you'll have to either be able to use a calculator like this that allows you to input the area and go to the probability, to the boundary, or you can use an inverse function like in the TI, the inverse norm is the way to go. And if anyone's trying to work with that, I recommend visiting my office hours. I'm happy to show you. I have plenty of experience with the TIs on how to use those. But I know you can do this also in the online StatBook calculator. There are other calculators out there that I'm less familiar with. I believe you can do it with Excel and Google Sheets as well. I know you can do it with Desmos. In fact, I created one because I had some students who were trying to use Desmos to do it. Not easy.
Isn't there one in Wagner's list as well?
Yeah, the one in Wagner's is the one we were just using right here.
Okay.
That's what you want to do most likely if you're using Wagner's. You can do it using Desmos. Basically, I created a normal CDF function, and I can solve for when that normal CDF is equal to a certain value. Turns out the normal CDF is, if you've taken calculus, you've probably seen this before, it's an integral. It's the area underneath that PDF function for the standard normal distribution. So this is that area, and what this does is it computes probabilities, and if I wanted to find what's the 75th percentile, I have to use this calculation to find out where they happen across. And the 75th percentile on the standard normal distribution is at a z-score of 0.674. Okay. Now, just because you can do it that way doesn't mean you should. I did this just to show that it could be done, and if you want to use it, I'd be happy to share it with you. but I would strongly encourage you to use something a little bit simpler. This is much easier to interpret, much easier to avoid making mistakes when you're inputting answers in this form. All right. Questions on the critical values? Well, let's move forward. In order to do a confidence interval for proportions, I need to be able to assume that the sampling distribution follows that normal distribution. And if you recall from before, when we used the central limit theorem for proportions, we had to assume a few things. We had to have a few conditions that were satisfied before that distribution would apply. So in order to build these confidence intervals in the same way, we still need to check those same conditions. Now remember, those conditions are the independence assumption, the 10% condition, and for proportions, the success or failure condition. Does anyone remember what those are? What is the independence assumption?
The sample has to be independent of the population.
So the sample has to be independent of, I didn't hear what the last part was.
Of the population value.
Okay. We don't want the sample necessarily to be independent of the population. In fact, if anything, we want it to be representative of the population, so that would kind of not be independent. We want it to be like the population, if possible. The independence assumption is referring to individual members of the sample. And so, for instance, if I'm doing a survey, I want to know that the answer that person number 5 gives me to whether they support Congress or don't is independent of the answer to person number 6, or person number 7, or person number 250. Right? I want all of those different results to be independent of each other. That's really hard to guarantee, especially if I'm surveying a small area. It's possible I'll be calling people who are somewhat connected to each other. Maybe they are majoring in the same major at UMA, and I happen to collect both of those people, so they know each other, they talk to each other a lot, they might have similar political views. That's not going to make them necessarily independent. It's hard to control for that because of so many different ways it can be violated. How do we usually check for the independence assumption? Remember?
1 minus?
That's the complement rule.
Okay.
How do we check that the independence assumption is satisfied for our sample? So usually the easiest way to do it is the randomization condition. If the sample has been collected with sufficient randomization, then we're going to assume that that gives us independence of the individual results. So if I'm doing a survey, as long as I have a large enough sampling frame, that is a large enough number of people I could potentially poll, and I have a good process for randomly selecting a subset of that frame, then I'm going to assume that that by itself gives me relative independence of the individual responses. I'm not calling one household and then asking them for every adult in the house to respond to this poll. Those will be connected to each other for obvious reasons. If I'm randomly selecting from a large enough sample frame, then that randomization by itself should give me a reasonable amount of independence. What about the 10% condition? What does that say?
The sample size needs to be less than 10% of the population.
Good. So the population I'm trying to understand, I need to make sure that my sample size is smaller than 10% of that. Now, in the case of, for instance, the survey about Congress, I need to make sure that I am surveying less than 10% of American adults. That's pretty easy. 10% of American adults would be a lot of people. And so I'm probably not doing a poll with, what would that be, 35 million people. That's an unwieldy poll, so that's not going to happen. Don't have to worry about that part. On the other hand, if I'm trying to understand, say, a student government representative election at UMA, then 10% of the population might actually be a number that I could inadvertently hit. So I want to make sure that I avoid doing that if I'm trying to understand how that election might turn out. What about the success or failure condition? What does that say?
We have two outcomes, success or failure.
I have two outcomes, success or failure, and specifically in my sample I need to observe at least 10 successes and at least 10 failures, or expect for that to happen if I'm using an estimate from the population. So in the case of the congressional poll, we had 230 respondents, and 19% said they supported it, 81% said they did not. I just need to make sure that 19% of 230 is bigger than 10, and 81% of 230 is also bigger than 10. And of course, in practice, I just need to check the one of them. If 19% of 230 is bigger than 10, then 81% will also be bigger than 10. It only goes in one direction. All right, so those are the three things you do have to check. If you don't have those, then we can't assume that the sample distribution is a normal distribution. And from that, we then cannot use the reasoning we used to construct the confidence interval. But usually it's not terribly hard to do this. The 10% condition just means that your population is not very small, even if your sample size is big enough. And if your population is small, then you probably just want to actually survey most of the population and just report that without constructing a confidence interval. On the other hand, if your population is big, then this is pretty easy to satisfy. You should always use randomization in constructing your sample. Do everything you can to avoid any potential sample bias. And then this condition is also pretty easy to check. You simply need to make your sample size large enough to expect at least 10 successes and at least 10 failures with reasonable values for the success rate. Okay. All right. Suppose, as I said before, I'm trying to find a particular margin of error. I want to estimate the support level to within, say, 2% as a margin of error. I can use the margin of error formula, plug in the margin of error I'm looking for, plug in the confidence level, and therefore the critical value that I need for that confidence level, and use the worst case scenario for the p hat and the q hat, right? If my p hat is 80% and my q hat is 20%, this margin of error will be smaller than if my p hat and my q hat are both 50%. The worst case scenario is when p hat and q hat are both 50%, so if I use that, I can find the sample size I need to guarantee the desired margin of error. If I choose more people, or if my success rate happens to be further from 50%, in both cases my margin of error will go down, and so it will fall under the amount I'm trying to be within. So here's an example. Suppose I'm doing a confidence interval for proportions, maybe it's a survey, and I want to guarantee that my margin of error is 4% or less. If I'm doing a 95% confidence interval, I can find the sample size that I need to guarantee that. So let's walk through that process. I'm going to use the formulas that are on this page, this formula, and I'm going to use a 4% margin of error. Okay, so let's do that. Switch over to the document cam here. So I want the margin of error to be 0.04. I want my critical value to be 1.96. And what I'm going to use for my worst case scenario is a success and a failure rate of 50%. If they are anything else, if this is 40%, this would be 60%. 0.4 times 0.6 is less than 0.5 times 0.5. So my margin of error will be even smaller. This is the worst case for the margin of error, so that's what I'll use to compute the necessary sample size. And so what I want then is, what is the end value that I need?
So let's write down the
formula.
Margin of error.
Margin of error is
Z star,
the critical value,
times the
standard error,
which is p hat
times q hat
over n,
all under the radical.
Now I
have a value for this,
for this,
and for this, meaning n is the only thing I don't have a value for, And that allows me then to solve for n if I plug everything in and solve the resulting equation. This is going to be a little bit more difficult, however. It's not a linear equation. It's not one of the simple equations we did in algebra. It's one of the more complicated ones. But we can still solve it using those same ideas. So let's do it. 0.04, that's my margin of error, is 1.96 times the square root of 0.5 times 0.5 over n. Okay. How would I solve this for n?
Radical first.
I want to get the radical by itself first. So what do I need to do to make that happen?
Can't you square those sides?
I will want to square both sides, but it's going to be a lot you can do it this way, but it'll be a lot easier if I square it when the radical is by itself. Because then all that happens on that side is that the radical goes away.
So under the radical, you want the 0.5 times 0.5?
Yep, that's still there. Oh, you mean to calculate that? I can do that, yeah.
Do that first.
.5 times 0.5 is 0.25. Right, 1/2 times 1/2 is 1/4. Now, as I said, I could square both sides at this point, but I have to be careful because of the way the 1.96 and the square root both interact. It's actually probably easier if I get the square root by itself before I square. So how do I get rid of this 1.96 here?
Divide both sides.
Alright, divide both sides by 1.96. So I get 0.04 over 1.96 equals the square root of 0.25 over n. Well, let's see. 4 over 196 is 1 over 49, I think. Right? Well, I'll leave it that way. You don't have to do it that way I was just about to do it. I've isolated the radical, so now I want to square both sides. If I square the right side, all that happens is that the radical goes away. So I can tell that I'm getting closer, but I still don't have n equals, which is what I want. How do I get n equals here? Well, one thing I notice, I have a fraction on both sides. And the part I want is in the denominator on one of those sides. So it turns out what I can do is I can actually flip both fractions upside down. If they're equal to begin with, then when I flip them upside down, they'll still be equal. The technical term is taking the reciprocal, or taking 1 over each side, or raising both sides to the negative first power. They all do the same thing. The effect here is this fraction gets flipped upside down, and so does this one. All right. How do I go from that to a value for n?
Can I ask a really silly question in regards to when you were just at that previous step? Why didn't you cross multiply?
Oh, you could cross multiply if you'd like.
Okay.
The problem is I haven't squared both sides here, or squared both the top and the bottom. So I don't literally have a fraction equals a fraction. I have to simplify this before I can do it that way. If I wanted to do that, that would work. And in fact, I'll show you the result that comes from that in just a moment. Well, if I have n over 0.25, and what I want is just n, all I have to do is multiply both sides by 0.25. On the right, when I multiply it by 0.25, it just gets rid of the denominator, and I'm left with just n. And on the left, I have 0.25 times 1.96 over 0.04 squared. So now it's just a matter of calculating that. Let me quickly see what comes up on the calculator. 1.96 over 0.04 is 49. Okay. 49 times 49 times 0.25 is 600.25. So that means to guarantee a margin of error of 4% or less, I need to have at least this many members in my sample. So what number should I report as the answer?
$600.
Not just 600.
Greater than or equal to 600?
Yeah, I need an integer that's at least 600.25. So I always have to round up to the next person. Right? If I'm surveying, I can't survey just 600 people because that won't quite be enough. But I also can't survey 604 people. That 1/4 of a person doesn't really count as a survey. So I have to survey 601. Okay, so 601 is what I need to have as my sample size to guarantee a margin of error of 4% or less. Chances are I'll fall well under the 4% range because I only need 600.25, and even then, that's only in the worst case scenario when I see 50-50 support and not support. If I see 30-70, I'm going to be far away from the 601, so in fact, a lot less will be necessary to get a 4% margin of error. But before I do my survey, I don't know what to expect, so I have to assume the worst case scenario to guarantee the margin of error I'm looking for. Okay. All right, any questions about that? Make sure that
Any of the calculators on Baldmar's calculators that we could use to confirm this?
There is, and in fact, I'll show you that in just a moment. First thing I said I would show you how to do the cross multiplying too, so let's do that before we go any further. Yep, there we go, 601 is what I found. So you were asking when we had it as 0.04 over 1.96 squared equals 0.25 over n, can we cross multiply? And we're close to that. What we'd have to do is to square the numerator and square the denominator so that we have fraction equals fraction, and then we can. 0.04 squared, let's see, that'd be 0.0016. 1.96 squared, I do not want to do in my head. That is 3.8416. So at that point, I have fraction equals fraction, and that's when I can cross multiply. So this numerator times this denominator equals this numerator times this denominator. And if I divide both sides by the 0.0016, just double check, but I should get the same 600.25. Yep. When I evaluate this, I get 600.25. There are multiple ways to go from the initial equation that we started with here to this final solution. This is the way I typically use because this is guaranteed to work, and it also makes the squaring process as simple as possible. But if you connect better with the cross multiplying, by all means do it that way. You'll still end up at the same place. Okay. Now there was another question a moment ago, which I feel like I've forgotten already. What was the question?
It was to confirm that we're right. Was there a calculator on the bottom?
Yes. Thank you for asking. So let's go back to Bognar's calculators. And thus far we've been using mostly his distribution calculators. We used his binomial distribution and Poisson distribution among the discrete ones. I'll minimize that. Among the continuous ones, we've used the normal distribution. And later, at the end of this discussion, or more likely at the start of the next one, we'll talk about that student's t-distribution. So both of those are here as well. What we're doing right now is we're trying to take a sample and from that construct an understanding about the population. That's what the process of inference is about. And so the statistical inference calculators are about what can we infer about either the population mean or the population standard deviation, or the population proportion. Right now we've only done proportions, so let's click on this one. And if I used 601 in my sample, and I had a 50% success rate, I would get 0.46 and 0.54 as the boundary points, which is a margin of error of exactly 4%. So this is constructing my confidence interval in that interval notation form. Okay. And later, when we do hypothesis testing, this is the place where you can input your hypotheses and test those at the desired significance level. You want to see the equations involved? They are taking the critical z-score. The central point came from our sample, which is 50% since we're doing the worst case scenario. The critical score, which is the 1.96, times the square root of p hat times q hat. Remember, that's always 1 minus p hat over n. When we did 600, that worked. Curious if it will allow me to do 600.25. Nope, it won't. That's just as well. We don't want that to be a viable possibility, excuse me. We do 600, then I get a margin of error less than 4%, so here's that margin of error in that form. Do 600, it's slightly more than 4%. So 600 is not enough, 601 is enough. Does that help? Excellent. And I would recommend using this calculator to construct your confidence intervals, but there will be a few places where you need to be able to solve for something related to the margin of error, and that will require you to be able to use these formulas. So that's why I'm using the formulas in the discussion, but you can use the calculator to save yourself some time. Make sure you know how to interpret things correctly, and also make sure you know how to check the conditions that are necessary for it to apply. All right, questions about that? We've gone a bit longer than I usually like to go before our first break. It's 10:37, so let's take a 5-minute break. I feel fairly confident we will not cover the third portion of this today, but we should have time for the second. We'll return at 10:42, and I'll see you in 5 minutes.